Let us begin with the module on TTL logic family, that is transistor logic. In this family, transistor is basic building block. Different parameters which are associated with these logic families are also seen in this module. They are propagation delay, fan in, fan out, power dissipation, etc. The speed power product, that is the figure of merit that we have already seen in the previous module, is also discussed for this logic family. Different types of TTL logic families are discussed in this module. They are compared on the basis of their performance parameters. Handling the unused input is important aspect related to the TTL logic family that is discussed in detail. At the end, data sheets associated with TTL logic families are also discussed. Learning objectives. In this particular module, we are going to see about the TTL logic family, understand working of basic logic gate in TTL, classify TTL logic family into subfamilies, different output configurations of TTL logic gates, comparison of TTL subfamilies based on their performance parameter, how to handle unused inputs of TTL logic gates. Consider the internal schematic of TTL logic gate. It has three parts: input stage, phase splitter and output stage. In the input stage, it consists of a transistor which is multi-emitter. Two inputs A and B can be applied here. These are logic 1 and logic 0 and their combinations. In the second section, that is phase splitter, the transistor is used as a switch and it splits the phase into two parts, that is 0 and 1, that is logic 0, logic 1. The third part, that is output stage, consists of two transistors, the upper one and the lower one. Both the transistors, they are not on at a time. You can see it when you see the working of this particular logic family. They are called as totem pole arrangement. We can see this in detail in the preceding section. Let us see the working of TTL NAND gate. You can see on the slide different transistors, resistors and diodes. According to the internal schematic of the NAND gate, this particular diagram can be splitted into input stage consisting of transistor Q1, diode D2, D3 and inputs A and B. Phase splitter stage is indicated by transistor Q2 along with the resistors R2 and R4, and the output stage consists of transistors Q3 and Q4 along with the resistor R3 and diode D1. Let us see the working of this particular NAND gate. If input A and B both are logic 0, then the multi-emitter transistor Q1 is on and therefore the output is logic 0. If you change the inputs to logic 0, that is input A is logic 0 and input B is logic 1, then again transistor Q1 is on, Q2 is off, which splits the phase into logic 1 at collector and logic 0 at emitter, and transistor Q3 will be on while Q4 will be off, and hence output is logic 1. If input A is logic 1 and input B is logic 0, then Q1 will be on, therefore output is logic 0, Q2 is off, collector is at logic 1 and emitter is at logic 0, and therefore again Q4 is off and output is at logic 1. If input A is at logic 1, input B logic 1, here now transistor Q1 will be off because the emitter base junction of transistor Q1 is now reverse biased. This makes the phase splitting to change from collector to logic 0 and emitter to logic 1. Due to this, transistor Q3 is off and Q4 is on, and hence the final output Y is at logic 0. Let us see different types of TTL logic families. TTL logic families are classified based on their output configurations. They are open collector, totem pole or standard output, and 3-state or tri-state output. Let us begin with the totem pole configuration considering TTL NAND gate. As discussed earlier, it has 3 stages consisting of transistor Q1, Q2, Q3 and Q4. Here Q3 and Q4 are in the totem pole configuration. This is the output configuration where Q4 is at the bottom and Q3 is on the top as shown in the animation. This output is therefore called as totem pole output. Let us see what are the disadvantages of totem pole output configuration. As seen on the diagram that there is a gate, and to the output of this gate number of loads are connected. If the output configuration is a totem pole configuration, then such loads cannot be connected. So, we are not able to connect outputs of totem pole devices together. Such connection is impractical connection. Let us see second type of output configuration, that is open collector output configuration. Again you can see that here the upper transistor is absent. So, the output of Q4 is open. It is not connected to power supply, that is plus VCC, and hence this configuration is called as open collector output configuration. Advantage of this configuration is wired ANDing, which is not possible in totem pole output configuration. You can see that Q4 as the output stage of one TTL device, which is connected to the output stage of second TTL device. Resistor is required to be connected from the collector of transistor Q4 up to the VCC. This will also allow the current to flow from the output stage of one type of gate to the other TTL gate. In this way, number of TTL gates, their output stages can be connected together. This particular phenomena is called as wired ANDing. Such configuration is not damaging the output stages of TTL logic gates, and it also gives optimized performance. Third type of output configuration is tri-state output configuration. There are 3 possible output states: logic 1 state, logic 0 state and high impedance state. High impedance state is a state in which the output remains inactive irrespective of variations at the input. This high impedance state is controlled by external enable input. This enable input is active or high impedance state. When we say active, logic 0 or logic 1, and high impedance state means cut output stage from the gate. Advantage of such output configuration is parallel connection of their inputs and outputs to a common bus line. Let us see how this tri-state output configuration works. This particular circuit is of TTL inverter circuit. That is, if you consider their Boolean equation, then output is inversion of input. It has two inputs, A and enable. This enable input enables the TTL inverter to work as an inverter or in the high impedance state. Let us consider enable as logic 1 and input A as logic 0. As this circuit is of inverter, expected output is logic 1 because input A is logic 0. Because A is logic 0, transistor Q1 is on because its emitter base junction is forward biased. Because Q1 is on, output is logic 0, which makes the transistor Q2 off. Because Q2 is off, output at the collector is logic 1, while at the emitter it is logic 0. This makes the transistor Q3 on and Q4 off. So, the final output Y is logic 1 when input A is logic 0. So, enable equal to 1 really enables the gate to work as a TTL inverter. Let us see the another condition, that is when A is equal to logic 1. Enable, again it is logic 1. So, here because input A is logic 1, emitter base junction of Q1 is reverse biased and therefore Q1 is off. Because Q1 is off, Q2 will become on because the collector of Q1 is at logic 1. Because Q2 is on, therefore the output at the collector is logic 0 and at the emitter it is logic 1. So, Q3 will be off and Q4 will be on. So, the final output, that is Y, is at logic 0. Therefore, we can see in the previous slide, when input A is 0, output Y is logic 1. When input A is logic 1, output Y is logic 0. And in both the cases, enable is logic 1. So, enable is equal to logic 1 enables this particular logic gate. Now, let us see how it works if the enable is 0. When the enable is 0, diode D3 is forward biased. So, it will be on. If input A now is logic 0, this will make the transistor Q1 on, which makes Q2 off. But because enable is 0, Q3 is also off and Q4 is also off. So, we cannot determine what is the actual output value for Y. Similar is the case when we consider the input as logic 1. So, if enable is logic 0, then both transistor Q3 and Q4 will be off in that case, and hence you cannot determine the output, and hence we say that output is in the high impedance state. We have seen the classification of TTL family on the basis of the output configuration. Now, we again classify it on the basis of their performance parameter, which is the figure of merit. Figure of merit is generally defined as a speed power product. That is, it is related to the propagation delay and the power dissipation. It indicates different possibilities of achieving optimized figure of merit. It can be implemented by using different TTL subfamilies, that is, slight variation in the figure of merit is observed in different TTL subfamilies. Subfamilies are, we know that there is a standard TTL, low power TTL, high speed TTL, Schottky TTL, low power Schottky TTL. These are different subfamilies based on the performance parameter, that is figure of merit. In one of the family, power is reduced, while in another family you can see the speed is increased, that is propagation delay is reduced. In low power Schottky, power dissipation is less and the propagation delay is comparatively less. Let us see what are the parameters or the characteristics of these different TTL subfamilies. Consider standard TTL. It uses resistors, lower power dissipation, propagation delay largely depends on the storage time and the RC time constant. In low power TTL, resistor values used are generally higher than that used in the standard TTL. It reduces the power dissipation but increases the propagation delay. In high speed TTL, low resistor values are used. This reduces the propagation delay but increases the power dissipation. In Schottky TTL, non-saturating bipolar logic is used, removes the storage time of transistors by preventing them from going into full saturation. Speed of operation increases without excessive increase in the power dissipation. Propagation delay is of the order of 2 nanoseconds. Low power Schottky TTL sacrifices some speed, has reduced power dissipation. It has same propagation delay as the standard TTL, but the power dissipation is about 1/5 of that of the standard TTL. Most popular version in new digital circuit system design. Let us compare these TTL subfamilies based on the propagation delay, power dissipation and figure of merit. We can see their actual values. If you consider standard TTL, then its propagation delay, that is expressed in nanosecond, is 10, power dissipation expressed in milliwatt is 10, and therefore their speed power product, that is figure of merit, is 100. Low power TTL, abbreviated as LTTL, propagation delay 33 nanoseconds, power dissipation 1 milliwatt, speed power product 33. High speed TTL, abbreviated as HTTL, propagation delay 6 nanosecond, power dissipation 22 milliwatt, figure of merit 132. Schottky TTL, STTL, propagation delay 3 nanoseconds, power dissipation 19 milliwatt, figure of merit 57. Low power Schottky TTL, abbreviated as LSTTL, propagation delay 9.5 nanoseconds, power dissipation 2 milliwatt, figure of merit 19. Let us see some examples of these TTL logic subfamilies. If you consider standard TTL, then its prefix, that is, it is identified by the series 74. Some examples are 7402, 74193, etc. High power TTL, its prefix is 74H. Examples are 74H02, 74H193, etc. low power TTL, prefix 74L, examples 74L02, 74L193. Schottky TTL, prefix 74S, example 74S02, 74S193, etc. Therefore, generally 74 series is used for commercial applications and 54 series is also used for the military applications. This slide shows typical values of different parameters which are associated with logic family for 5400 or 7400 series, 54H00 or 74H00, 54L00, 74L00, 54S00, 74S00, 54L00, 74LS00, and their units are also given. Parameters are VIH, that is when the input is high, you can see the high input is considered as 2 volts if you consider 5400 or 7400 type of TTL logic gates. Then VIL, that is low input voltage, is 0.8 for 54 and again 0.8 for 74. VOH, that is what is considered as the high output voltage, it is 2.4 volt for both 54 series and 74 series. Output voltage low is 0.4 for both the type of series. High input current is 40 microampere, then low input current is minus 1.6 milliampere. So, in this way different parameters are listed in this particular table. This slide shows typical values of certain parameters of TTL subfamilies. VIH, input voltage considered as logic 1, VIL, input voltage considered as logic 0, VOH, output voltage considered as logic 1, VOL, which is considered as low output voltage, IIH, input current considered as logic 1, IIL, input current considered as logic 0, IOH, output current considered as logic 1, IOL, output current considered as logic 0, ICC for logic 1, ICC for logic 0, TPHL and TPLH, these together form the propagation delay for the gate. Logic families such as standard TTL, high power TTL, high speed TTL, low power TTL, Schottky TTL, low power Schottky TTL, etc. are given in the column. The last column shows the units in which these parameters are expressed, like voltages are expressed in volts, all currents are expressed in microamperes, milliamperes, and the propagation delay is expressed in nanoseconds. If you consider the standard TTL 7400, VIH is 2 and it is 2 for all the TTL subfamilies. VIL is 0.8 for 7400 and 74H00 series. It is 0.7 for 74L series, 0.8 for 74S and 0.7 again for 74LS. Values for 54 series and 74 series are almost same. VOH for 74 series 2.4, 74H series 2.4, 74L series 2.4, 74S series 2.5 and 74LS series 2.5 volts. There is a difference in these values for 74S series of 5-4 and 7-4 series. It is, if you consider 5-4 and 7-4 series, then for 5-4S and 7-4S there is a difference in the values of VOH 2.5 and 2.7 respectively. VOL for 7-4 series it is 0.4, 7-4H series 0.4, 7-4L series 0.3, 7-4S series 0.5, 7-4LS series 0.4 volts. There is a difference in their values for 5-4 and 7-4 for 7-4L series. It is 0.3 for 5-4 and 0.4 for 7-4. Again for LS series it is 0.4 for 5-4 and 0.5 for 7-4 volts. IIH values are 40 for 7-4 series, 50 microampere for 7-4H, 10 microampere for 7-4L, 50 microampere for 7-4S, 20 microampere for 7-4LS. IIL minus 1.6 for 7-4 series, minus 2 for 7-4H, minus 0.18 for 7-4L, minus 2 for 7-4S, minus 0.36 for 7-4LS. It is expressed in milliamperes. IOH 7-4 series 16 microampere, 7-4H 20 microampere, 7-4L 2 microampere, 7-4S 20 microampere, 7-4LS 4 microampere. IOL it is 16 milliampere for 7-4 series, it is 20 for 7-4 and 5-4 series, 2 and 3.6 for 5-4 and 7-4 series respectively, again 20 for 5-4 and 7-4, and it is 4 milliampere for 5-4 series and 8 milliamperes for 7-4 series. ICC for logic 1 is 8 for 7-4, 16.8 for 7-4H, 0.8 for 7-4L, 16 for 7-4S and 1.6 for 7-4LS. It is expressed in milliampere. ICC for logic 0, it is 22 for 7-4, 40 for 7-4H series, 2.04 for 7-4L series, 36 for 7-4S series, 4.4 for 7-4LS series. It is expressed in milliampere. Value of propagation delay when it goes from high to low is 15 nanosecond for 7-4 series, 10 nanosecond for 7-4H, 60 nanosecond for 7-4L, 5 nanosecond for 7-4S and 15 nanosecond for 7-4LS. And TPLH, that is when it goes from low to high, 22 nanoseconds for 7-4 series, 10 nanosecond 7-4H, 60 nanosecond 7-4L, 4.5 nanosecond 7-4S and 15 nanosecond 7-4LS. Some typical values of fan out of these logic families are given. That is, if the source is a TTL device and the load is also a TTL device, then how many devices can be connected is given in the tabular form. Let us take one example, that if the source is 5-4 series or 7-4 series and load is also 5-4 or 7-4 series, then maximum number of gates that can be wired together are 10. If it is 7-4H series, it is 8. If load is 5-4L series or 7-4L series, then it is 40. If the load is 5-4S or 7-4S series, it is 8, and 5-4LS or 7-4LS as a load, then 20 different gates can be connected together. So likewise, if the source change, then according to the load, the fan out also changes. Let us see how to use the unused inputs of TTL. In the diagram, you can see 3 input NAND gates. A and B are the used inputs, while the third input in red is unused input. This unused input is treated as logic 1. If you say y is equal to a dot b dot 1 bar, that is equal to a dot b bar. In case of AND gate, this unused input is treated as logic 1. So, the Boolean expression for that is y is equal to a dot b. Sometimes this particular unused input is connected to plus VCC through resistor. Resistor of 1 kilo ohm is generally used to protect the input from power supply spikes. However, if you consider the logic gates such as OR gate or NOR gate, then this unused input may create a problem. Say in case of the first type of OR gate, where A and B are inputs and the third input is unused, then output Y is A plus B plus 1. So, there is always 1 which comes at the output even if A and B both are 0, 0. So, such type of input can be connected to ground. If you consider the NOR gate which is connected to it, then this output Y is A plus B bar if the unused input is connected to ground. Even if you connect it to the other used input, the output equation, which is the Boolean equation, is not altering. Similar is the case for the NOR gate and the NAND gate. Let us summarize this module on transistor logic family. We have seen the internal schematic of this logic family consisting of 3 stages: input stage, phase splitter stage and the output stage. We have also seen the different types of this logic family such as standard TTL, low power Schottky TTL, etc. We have compared this logic family on the basis of figure of merit, or we can say their performance parameters. We also saw that how the unused inputs are handled. They have to either connect to plus VCC or they should be connected to ground. One of the most important feature of this TTL logic family is wired ANDing. It enables the wired ANDing because of the different type of output stage called as open collector. We have seen totem pole output stage, open collector output stage, Tristate output stage. In case of Tristate, we have enable input, otherwise it is a high impedance gate. We have also seen how these are used for different purposes. Lastly, we have seen how the data sheets are arranged in this particular logic family.